So let's start with the solutions to the assignments, the last week assignment. And we had basically two spaces. We have the office and then we have the classroom. So the first thing, we are calculating ventilation load. So at the end, you see that the results or the energy that you have to consume in the office space with only 5 people is higher than the energy that you have in the classroom with 30 people. This is wrong. Okay, so and this is common sense. You might have a mistake in calculations in units or whatever, but at the end you write down the results and you see that the heating loads or the cooling loads of a space with fewer people is higher than the heating load of a space with a lot of people. There's something wrong with it. Everything depends on the number of people. The more people we have, the higher the heating or cooling loads for ventilation. So that's the first thing that we have to analyze. Then we have to do this in summer and winter. Interior conditions are always the same. The airflow rate is 20 CFM per person. We have 5 people. So the CFM here times 5, that will be 100 CFM. And now, if we want to introduce this data into the psychrometric chart, first we have to go to settings. English units, reset input, submit. Okay, there you go. Okay, so I'm sure that some of you got this number with CFM and just typed 100 CFM here. Be careful with units, okay? So because here we have pounds per hour, and how we turn pounds per hour into or CFM into pounds per hour. I'm going to do it again. CFM is cubic feet per minute. So we have to multiply times 60 minutes per hour, and we cancel minutes, and we have hour. And then we have to cancel cubic feet, and we need pounds here. So divided by cubic feet. And what is this? This is the air density. So the air density, we have here if we are in basic units or basic, here we have the air density in pounds per cubic feet. We just have to type here something and submit. And the air density depends on the conditions, but it should be close to this, close to 0.073. 73 pounds per feet. If we look at air density in pounds per cubic feet, it's look at this. This is 0.7. I have found this. So that's wrong. Okay, so these are not the units that we have to use because it should be 0.07. Why do we have this? I don't know, but some of you, I'm sure that you have typed here 0.7, and when I checked it, I found that the first value I get is this 1.7, and it's wrong. So sometimes you can't trust the first value that you get on the internet or in Google. So these are the units that we are using, and it's pounds per cubic feet, and here we have pounds per cubic feet. Quite easy to remember. Wow. So I go to a converter. So the converter density kilograms per cubic meter to pounds per cubic feet. Converter, this one. Okay, so if I have 1 here and I convert, this is 0.06. Okay, so it's close to 0.07. Actually, my teacher was wrong because the air density is 1.2. So if we do this, it's a 0.075. Okay, it can be 0.074, 0.07. The third decimal doesn't matter, but the first decimal in this case matters. Okay, so when I have this, I Google air density and I have 0.7. But in this, I have 0.07. So what's the right one? This, I know that this is the right number in international units, and then this should be 0.07. Be careful with that, okay? So the units are important. So the air density is always 0.07. So now if we have 100 CFM, we have to multiply 100 times 60 times 0.073. And that's the airflow rate in, so times 60 times 0.07476, I don't mind. And then the airflow should be 100 times 60 times 0.074. So it's around 444 pounds per cubic feet. Okay, it's a question of units. So now, well, I don't mind. It can be 444 or 450. I don't mind. The difference, it's not that much. But if this is not 0.07, it's 0.7. Now this would be 4,000, not 400. And then we are making a huge mistake. If we are here in process, the first condition is 30 and relative humidity 80. This is 70 and 40. 70 and 40. Now we compute, submit, and the cooling, the heating load, it's 400. No, because I didn't. Okay, so I have to type here the right value for the airflow, 400. Okay, yeah. So you have to be careful. 4.7 and 4.7. And now submit again. And this should be 102. And here we have 102. Okay, so that's it. But these are BTU per minute. Again, we have different units here, and we need BTU per hour. So we have to multiply times 60, and here we have 6,000 BTU per hour. If we keep this condition for 12 hours, we multiply this times 12, and 73,000 BTU. It's the energy that we need. Okay, so there are a lot of, we can make a lot of mistakes here. First, the air density. If this number were 1, it would be easy to remember, but it's not 1. It's 0.076 whatever in pounds per cubic feet. Anyway, so that's the first. This is winter. In summer, we have the same. We have the same airflow. It's the same because that depends on the people. We only have different outdoor temperature. So the outdoor temperature is 125. We have the same airflow, and then we have different cooling load per minute, then times 60, and so I don't know. It doesn't happen always. It depends on the difference of temperature. So here in these conditions, we have 100 minus 70, so it's about 30-degree difference. And here we have 70 minus 30. So Usually when we have a higher temperature difference between indoor and outdoor conditions, then the loads should be higher. And this is what happens here. In winter, they are slightly higher, but if we have, yeah, so if this temperature were 40 or something like that, probably the summer loads would be higher than the winter loads. Okay, so if we are here, the flow rate is 20 CFM per person, that's fixed. We have 30 people, so that would be 600. The airflow rate is times 30 equals 600. 600 CFM times 60 times 0.074, I think. So that is 600 times 60 times 0.074. So this is 26.64 units, pounds per cubic feet. Okay, pounds per cubic feet. And if we count here, well, it's 2600, and here it's 2700. Yeah, it depends on the decimals, because here I took 0.763, the same value that I got, well, this chart. Okay, so that's tricky, but that happens. Okay, so if I make a mistake with the decimal here, it matters. But if I make a mistake of 100,000 here, it's not relevant. Anyway, so that's it. We introduce this data here, exterior conditions, interior conditions, and so around 400,000 BTU. It's the classroom winter heating load. The cooling load in summer is around 386,000. So again, winter is slightly higher than summer. And yes, this value that we get in Google, when we type air density in BTU in pounds per cubic feet, it's wrong. It's from Wiki. What is that? Yeah, so, and then but you need to find your own. Okay, so this is true, and I know that's true because I learned it by heart. Okay, so I don't rely on Google, I don't rely on Wikipedia, whatever. I know this is true because I have read thousands of books, and the air density in international units, it's always 1.2 kilowatts per cubic meter. Okay, so that's the first thing that I wanted to talk about today. The second thing is that what we are doing. Okay, so why are we doing this? What's that? What are we calculating? Why I'm using air handling units? Where air handling units, we need air handling units in commercial buildings for ventilation. That's mandatory. And what are we doing here? We are calculating the ventilation loads. So now it's working. And well, what I want to show you is what we are doing here. Okay, so I recorded this video, and I'm going to explain you what we have to do or what we are doing. So we have a space. In that space, we have people and we have equipment. So the first thing we need to understand is that we have windows and we have solar radiation. Okay, so there's energy entering through the window, especially if they are south oriented. We have this big arrow entering through the windows. Then what else we have? Inside we have internal loads or internal gains. And what does it mean? Well, it means that people, our body temperature is at 90 something in Fahrenheit, and the indoor air is at 70 Fahrenheit. So, and what about the computers? What about the equipment? We touch the equipment, not only computers, but refrigerators and vending machines. So everything is releasing heat to the indoor air. Okay, so those are the internal gains. And we need to be aware that we have a source of heat inside the building. So we are radiating heat to the indoor air. And those are internal gains. Okay, what's next? Now we have to calculate the winter heating loads. But the heat that we receive from the sun and the heat that we release, people and equipment that we release, these are our allies because we are losing heat through the walls, we're losing heat through the walls, the windows, and through the roof. Okay, so we are losing that heat. And what is that heat? It's the U value of the envelope times the area times difference between the temperature difference, indoor minus outdoor temperature. And finally, we have to calculate the ventilation loads, and this is what we are doing now. So we are calculating ventilation loads with the air handling unit. Okay, so we calculate ventilation loads, we have the supply and return diffusers. So this is what we have done in Revit. We have the air handling units on the roof. And then from that air handling unit, we have that connects the air handling unit to the supply diffuser, that one. Okay, so that supply diffuser brings that air at comfort temperature, so it can be 70 or 72 or whatever comfort temperature. And then we have the return diffuser. So the return is supply. And the other one is the return diffuser. So we have another duct that goes to the air handling unit. And there we have the heat recovery. Okay, so this return diffuser gets the air that it's at the same temperature, at the comfort temperature, 70, 72. And then we go to the air handling unit. We have this heat recovery, so we mix the air, and then we have the supply diffuser. But we have to take the fresh air. So we take the fresh air, the heat recovery. And we take the fresh air from outside. Okay. So this is what we are doing. What are the ventilation loads? The ventilation loads is the energy that I need to heat up this airflow, and the airflow depends on the number of people here, and we have to heat up this flow from the outdoor temperature up to the indoor temperature, the comfort temperature. So that's the ventilation load. But we have other loads. We have the load that we lose through the envelope of the building, and we have internal gains because of the people and the equipment inside the bathroom, and we have gains through in sunny days. Yeah, today I think it will be a sunny day. We will have gains through the southern windows. The southern windows are over there. This is a northern window, so we are losing a lot of heat through that window. But if we have a south window, the sun enters through that window. Okay, so at the end there is a balance between the energy we lose to the walls, windows, roofs, the energy we lose because of the ventilation, because we need to get rid of the air that we have here, and we need to supply fresh air, and supplying fresh air at outdoor temperature, it means that we are losing energy. Okay, if we have a heat recovery, we lose less energy, but in those exercises that we are doing, we are not having a heat recovery. We are considering that we have the fresh air, and then we heat up that fresh air up to the supply temperature, the comfort temperature. Without next week, we will learn how to calculate the energy that we save with heat recoveries. Yeah.
How much of the air that's returned is used, and how much fresh air is inside?
The fresh air is
Yeah.
20 CFM times the number of people.
Yeah,
That's
yeah.
the fresh air. And the return air.
Yeah,
is
is
the same.
it reused as well?
It's not reused.
Not reused, okay.
We take this return air,
Yeah.
20 CFM per person, to the heat recovery. And the heat recovery, we reuse the heat. We don't reduce the air.
Okay.
The air that we remove We don't breathe it again. It's still outside.
Okay.
But this heat, we transfer part of this heat to the fresh air. Okay, so this is 0 Fahrenheit, and this is 70 Fahrenheit. With this heat recovery, we make sure that the air here is 30 Fahrenheit. The 30, we have to keep it up to 70. Okay, but we don't reuse is not the right word. We recirculate the air, we transfer that heat, but we don't. This air we get rid of it. We don't breathe it again.
So
It's what?
repurpose.
Yes, it's read something,
Yeah,
but it's not.
something.
We use, it's that we, okay, so we have this air and we introduce that air into the room again. We don't do that. Okay.
Yeah.
So that's the fresh air, and this is the heat recovery. Now, how can we have to put numbers to all these things. Okay, so we are calculating the heating load. So with the heating loads, we have heat losses in the envelope, and this is the formula, the U value, the area of the envelope, and different temperature difference. We have ventilation loads. This is what we are calculating now with the air handling unit. But we have internal gains, and we have solar radiation or solar heat gains. So that's important, and you need to be aware of this. We have different, here we have plus, and here we have minus. So there will be moments, even in winter, in which we don't need heating. Why? Because the energy that we are losing, especially if we have a very efficient building with a lot of thermal insulation, with triple glazing, the energy that we lose from the envelope is not that much. And the ventilation loads, if we use a heat recovery, an efficient system, we can reduce these two heating loads. And if we maximize the solar radiation, for example, there may be days in winter in which we don't need heating. So if we design a good building and we take into account the energy that we lose and the energy that we gain, that's a zero energy building. If we add up the internal gains and solar radiation, and it's more than the heat losses in the envelope and ventilation loads, we have a zero energy building. Okay, so zero energy building is not about using incredible technology. No, it's about designing a good building. And if we have in winter a good solar radiation, so that's why we have a huge curtain wall on the south facade there, because it's gaining a lot of heat. And that's why we have an efficient envelope here with a lot of thermal insulation, but actually it could be better. But we have a triple glazing here because we want to reduce this. And then how can we reduce the ventilation loads? Using the heat recovery. And then we can maximize the solar radiation. And then in winter, we will have a balance and we won't need energy. In days in which we don't have any sun, it's extremely cold, for sure, we need a heating system. Okay, so maybe there are half the days we need a heating system, but in buildings like this, half winter days, probably we don't need heating, because with the internal gains and the solar radiation, we can balance the energy losses. So the ventilation loads, there is a formula. I don't know if you saw this last year, the airflow times the specific heat and the web out temperature. Okay, but it's not relevant for this course. In solar radiation, we have the solar radiation times the area of the window. So solar radiation, we have solar radiation, there is sun outside. In the area of windows, we can design the area of windows. And then the internal gains depends on the number of people and the equipment. What happens in summer? In summer, we have the same with the cooling loads. We have the same people, the same equipment. We have the same sun entering through the window, but we have the same internal loads. But the fresh air now, it's not cold, it's hot. Okay, so the fresh air can be now at 70, not at 70, but at 90 or 95 Fahrenheit. And now these arrows, they don't go outwards, they go inwards, because we have a different temperature. We have a hot temperature outside and 70 Fahrenheit here. So these arrows are going in this direction. And what about the ventilation loads? The ventilation loads, we have to pull down this air. This air is at 95, and then we have to pull down the air at 70. Does the heat recovery work? It does, because we are now we don't have well, we have air at 70 Fahrenheit in the return. And what we are doing is to reduce that temperature, and this is 95 and this is 70. Probably the temperature after recovery to be 80 something, and then we have to go from 80 to 70. Okay, so everything works, but now it's even more complicated in summer because if we look at the numbers, in winter we can have a balance between heat losses and heat gains, but in summer, when we have the cooling loads, everything is positive. Okay, so I have to add up everything. So in summer, it's impossible having a balance between energy gains and energy losses. So we have to add everything up. The thermal gains in the envelope, the ventilation loads to the air handling unit, the internal gains, the people in the equipment, and the solar radiation that enters here. Can I get rid of the solar radiation? I can. If I use here like an overhand or something like that, I can prevent the sun from entering the building. So this is what I have to do in summer. In summer, I should avoid solar radiations. Internal gains depend on people and equipment. So there's nothing I can do with it. Okay, get rid of people. If I have to use the building, we will always have internal gains. And in office buildings, when we have a lot of people working in a limited space with computers and lighting and a lot of machines on, internal gains are important. And solar radiation, this is up to our design. Okay, so in summer, it's more difficult. In winter, it's easy to understand. We need a lot of thermal insulation. We need sun in the south. Okay, but this southern sun that is helping us in winter, it's damaging in summer. So curtain walls are not a solution, because in cold climates we might say, okay, in cold climates curtain walls facing south, it's a good solution in winter, but not in summer. So we're going to design a building system with air handling unit. So the air handling unit, we will need a boiler and we will need a chiller, the boiler for winter, the chiller for summer. But this is just for the ventilation loads. Then we have other heating system, and we're going to use a hydronic system. And a hydronic system can be with a radiator or radiant floor. Okay, so this is what we are going to design in the building that we are selling in Revit. And finally, for cooling, we're going to use a split system with an air-to-air heat pump. Okay, so that's what we are going to end up having in Revit. Okay, so what are we going to do in Revit? We are done with the air handling unit and the ductwork, but now we have to connect things to the air handling unit. We're going to connect the boiler and the chiller, and that will be just for ventilation loads. But ventilation loads, it's not everything, because I have the other loads here. So for the ventilation loads, I use the air handling unit. Okay. But for the envelope loads, the internal gains, the solar radiation, especially in summer, we're going to use split system. This is what we have here. Okay, so what we are doing is to replicate the system that we have here. We have this split system with a heat pump, air-to-air heat pump on the roof, and have the split internal unit there. And well, we're going to add the hydronic system. We don't have hydronic systems in this building, but just to cover everything that we can have, we will design a hydronic system in that building. Okay. But this is what we are doing. So we are calculating ventilation loads. That's the only loads that we are calculating in this course, ventilation loads, and we will learn how to reduce those ventilation loads by using the heat recovery in the air handling unit. And then we will design a system like this. And I want to include everything in the system: the air handling unit, the boiler, the chiller, the heating system, and the controlling system with the heater. Then we will need a boiler here. This boiler can be either a condenser gas boiler or a pellets boiler. Okay, so but we need another boiler. Can we use this one? Probably we will try to adapt this boiler or connect this boiler to the air handling unit and then to our heating system. We can do that. And finally, we need something to reinforce, because with the air handling unit, probably it won't be enough, especially in summer. So we need this split system to provide extra cooling energy in summer. Okay, so this is what we are going to do. But the most important thing that you have to understand is we have 4 components when it comes to energy that we are consuming in a building. The envelope, it's a piece of cake, increase the thermal isolation, don't do anything else. Ventilation loads, use of heat recovery. Internal gains, there's nothing we can do because it depends on the use of the building. If we design this classroom for 30 people, there are 30 people. And the solar radiation, the solar radiation design matters because we have to maximize the solar gains in winter and minimize solar gains in summer. And this is about architectural design. It's not about anything else. Yeah, we can use a technology with things that move so that in summer they let the sun in, and in winter, not the other way around. But I don't believe in things that move in buildings. So let's design something that is fixed and it works well in winter and summer. Okay, so that's what we are doing. And that's the assignment. And finally, I want to start this lesson on cooling systems. Okay, again, we have monsters on our roofs, and those monsters can be it's a human being, something like those roofs. So it's like another building, it's like a three-story building that we have on the roof of another building. So those systems can be incredibly big. And what is this? This is a refrigeration tower. So this is the same cooling system that we have in nuclear plants. Okay, so we can, I don't mean that we have a nuclear plant in our building, but the same system that refrigerates a nuclear plant, we can have it in our building. So it's another huge machine like this one. Okay. Well, we are familiar with this. We have the air handling unit, we have supply. And then we have return. This is hospital. So in the hospital, probably the renovation rate is not 20 CFM, it's more because hospital is something that the air has to be in very good conditions. And here I have a lot of videos, so I found this. Website. Yeah. Okay, so I have uploaded those videos here because it's quite, I think it's quite clear what we are doing here. And this is what we're going to explain today. We have the air handling unit. Okay, so this is the air handling unit. There is a boiler. And the boiler, as you can see, is here we have the pump. So we pump the water, the hot water, after the heating coil of the air conditioning. And then we return this water to the boiler. This is what we're going to do on Friday. On Friday, we will place a boiler on the basement, and then we have to figure out how to include all these ducts, not ducts, those are pipes. So water, hot water pipes are something like this. Probably one of those refrigerant. Well, one of those will be hot water pipes, so it's not as big as an air duct, but we have to keep that in mind. And then for the so the boiler works in winter, but what about in summer? In summer we need the cooling coil here, and then we have to connect this cooling coil to a chiller. Okay, so here we have a water cooled chiller. A chiller is a heat pump, but a heat pump usually when we are naming something as a heat pump, it's something that we can reverse the cycle and we can use it for heating and cooling. And when we have a chiller, it's a heat pump that works only for cooling. Okay, but what happens inside the chiller is the same thing that happens inside the heat pump. The good thing of a heat pump is that we can reverse the cycle. Heating or cooling. Chiller, it's just for cooling. Okay, so we're going to connect this heat pump or this chiller. Here we have the water, so we go in this direction, we go up, and then we return this water, and then we cool it down again in the chiller. But this is not enough with this kind of chillers, and we need a cooling tower. Okay, so that cooling tower, we need another circuit, the green one, and we will connect that chiller to the cooling tower. So cooling tower is something good because basically it's something that cools down water almost for free. Okay, so we don't need energy to do this with the cooling tower. It has other issues. For example, if it's in contact with potable water, in cooling tower, there is a lot of bacteria, and if we end up drinking this water that comes from the cooling tower, we can have a lot of issues, health issues. So cooling towers work well in these non-potable water circuits because nobody drinks the water that goes from the cooling tower to the water chiller. But sometimes if we have a cooling tower in the circuit that is in contact with the water that we can drink, we can have some issues. Okay. And so here we have two systems. We have the water-cooled chiller, and we also have the air-cooled chiller. So with the air-cooled chiller, if I could get rid of these subtitles. Okay, so here we have the same system. We have two schematic view. This is the air handling unit. So the same air handling unit. This one. We have a heating coil, a cooling coil. The heating coil, we use the same boiler. So this boiler and this boiler, they are the same. We go from the basement to the heating coil, and then we return to the boiler again. And here we have the air cooled chiller. Okay, so we have the water cooled and the air cooled. So the water cooled are usually monsters that are in the basement, and then we need a cooling tower on the roof. This monster is just on the roof. So here basically we combine both things. We have a heat pump, and then we have something that interchanges heat with the air. So in this case, both things are on the same machine. What is the best thing and what is the worst thing? I don't know. For really huge and demanding building, I think this is more efficient, the water cooled chiller. But it has to be something very, a very large building. In this building, we have air cooled chillers. Why? probably they are cheaper. And here you have to duplicate the system. Okay, so you really use these water-cooled chillers when the building it's something that it's very demanding. In this building, for the air-cooled chiller, it was enough. Okay. Important things. The water-cooled chiller is something that is on the basement. The cooling tower or refrigeration tower, it's on the roof. And these air-cooled chillers are always on the roof. Okay. So this system, it's more complicated, probably more efficient, but in terms of architectural design, it's more complicated because we have part of the system that it's on the basement, and the other part of the system it's on the roof. Here, everything is on the same box, and they are always on the roof. Okay, so we have this MEP Academy, very nice thing. Okay, so that's what we have. So at the end, this is a building. We have this is the air-cooled chiller. Okay, it's on the roof. We have the heat pump here, and we release that heat, or we take that heat from the outer air. So that's why the air-cooled chiller has to be always on the roof. And we have a boiler. So this is we have a boiler, the basement, and then we have air handling units. In this case, I don't know, we can place air handling units on the floor. I will do that. So I will place air handling units on the roof as well. But you see that again, we have to connect the boiler to the cooling coil of this air handling unit, the cooling coil of that air handling unit, the chiller, we have to connect to the cooling coil of the air handling of 2 air handling units. And here we have the big box. So it's a variable air volume box. And we can connect this with this. Well, so this probably this box, it's the variable air volume box. And sometimes, in this case, it's connected to the heating that comes from the boiler. It can be connected to the cooling element that comes from the chiller, or we don't have to connect this. We do this because we need extra heat. So probably the air handling unit is not enough to provide us with all the heat we need, and then we need another heating coil here just to heat up the air that goes from this area. We can complicate this a lot, okay? But at the end, it's about connecting things. I have boxes, and I have to connect these boxes. And then we have to place those monsters either on the basement or on the roof. But and here, what we see, we are unaware. We are human beings here, and we see a false ceiling. Well, here we don't have a false ceiling, and we see the diffuser. Okay, so that's all we see. Usually, when we are in a building, we look up and we see, oh, there's a false ceiling with diffusers. But we have all of these ducts, pipes, interconnected. Okay, and this is something that people are unaware of. Probably we knew that there is something like this, and this is what I insist a lot. If you have this living area, you have this area for the ducts, there's something wrong here. Okay, so we can have even more space for the ducts, pipes, boxes, and everything that the living space that we use the village. Okay, but there is a world above the false ceiling, and there in the world that our clients will live is this one. Okay, well, in those videos, they explain how it works, and they explain, and sometimes you have a good ad that, yes, that is beautiful. But let's go back to this. Okay, so that's the other system. We have the water-cooled chiller. So the water-cooled chiller, it's always in the basement. And the refrigeration tower or the cooling tower, it's always at the top. And we have two circuits. We have the blue one, the blue circuits that goes from the chiller to the cooling coils of the air handling unit. And then there's the green circuit that goes from the chiller to the cooling tower on the top of the building. Cooling towers, I told you, it's something that refrigerates water or cools down water for free. But the setback is that we have to use water. We have to use water. Okay, so this is you can see that this is not a closed circuit. If you follow this pipe, it ends. Yeah, so it ends in the top, at the top of the cooling tower, and then it releases water. Okay, so it's basically we have a coil. So how does it work? We have a circuit of water, and then we have a coil. And this water is warm. Okay, we're not talking about temperatures because I don't have a good idea of what temperature we're dealing with. But we have to turn this into. So we have to cool down this water. Okay, so as the water is going through this coil, we have, let's say, a cold water. And how do we do it? We do it by pouring water. Okay, so this green pipe that comes here, it's like a shower, and it pours water on this coil. So we cool down this warm hot water. We cool it down by pouring water. So what happens with this water? It evaporates. So here we have water vapor. Okay, so this is what a cooling tower is. And when we see cooling tower, we see a white smoke coming out. But this is water vapor, so it's not harmful. It's not CO2, so we don't do anything wrong with it. But we have to waste a lot of water here. So if we are in places in which water is not like this, it's all raining. Doing this in southern latitudes with water shortages, this is not the best system. But if we're doing this with because we have plenty of water, that's very efficient because basically we're not spending any energy. So we can cool down this by pouring water, and then that water finds something that is warmer than this water here, and it evaporates. And what we see, it's a vapor steam going out. So when we see nuclear plant, cooling tower, it's this. Okay, so those are huge, gigantic cooling towers. And what are we doing? We are getting water from the core. It's very hot, and then we pour water here, so we cool down this, and it expels this white steam that it's not harmful. It's like a water vapor. Okay, so it looks scary. Oh, look at this! The chimney is expelling smoke. It's not smoke. It's water. Okay, so yeah, it looks scary, but it's just water. So the dangerous part of the nuclear plant is not this one. It's something that it's at the core of the. Okay, but those are huge, enormous. So basically, we have the same. We have a water coil, and we pour water here, and we cool down this coil, and the steam goes on. Okay, so we have these kind of things in buildings cooling tower. Okay, so it's basically the same. It's like a huge box, and you see that we have steam. It's not clear, but probably in other pictures we can see when they are working. Yes, when they are working, they are expelling the same water steam through this cooling tower. Okay, so again, it's not dangerous. I had a teacher that told me, maybe this is not always true, but it helps. When you have a chimney that is very thin, and the smoke that is going through it is like dark, that's dangerous. When we have something that is huge, and the smoke that we have here is white, it's not dangerous. Okay, so what air should be? So are you safer here or there? You're safer here because what you're breathing, it's just water. When you're breathing here, it has a lot of gases that are harmful. Okay, maybe it's not very scientific, but yeah, I think 80% of the time it can be true. Okay, so when we see something that it's a very wide or very thick column of something white, usually this is not dangerous. When we see something very thin and it's dark, it's something dangerous for breathing. Okay, so I have posted here different videos. All of them are quite good, and they will explain you how air handling units work, chillers with air handling units, and VAV and air handling units. So we're going to use all these in our Revit file. We know everything about air handling units, right? Then on Friday we will connect the chiller. Either, well, we will connect both. We can use both air cooled chiller and water cooled chiller to be aware of the differences. And then we need the VAV. Those are these boxes that are connected to the ductwork. Okay, so this ductwork, we have the VAV, and with this we control the flow that it gets to every single room. Okay, so we will try to work with these three elements in Revit. Air handling units, we have already done it, chillers, and finally these VAV boxes. So we will try to insert all these things. The cooling systems, well, so we're going to explain, or I'm going to explain two different systems here. This is the chiller, the cooling tower, or the air handling unit. This one can be divided into, this is a water-cooled chiller. Water-cooled chiller, plus cooling tower, plus air handling unit. And we can have here air-cooled chiller, plus air handling unit. Okay, so those are, it's the same system. We have the air handling unit, and we have chillers, water-cooled or air-cooled chillers. And then the other system, it's a ground source heat pump with the air handling unit as well. And we can work the radiant system, because if we are working with a radiant floor in summer, if somehow we connect the radiant floor to cold water, we are working with the radiant floor in winter for heating. But if we connect the radiant floor to cold water, we can have a source of cool in the same room. Okay, so everything is about systems. It's about connecting things. Okay, I have this box here and I have this here. What if we connect them? Is it good or bad? And if it's good, connect them. And then you have to design the pipes that connects this and that. But everything's about, and the more things are connected, the better, because it gives us flexibility. It's more complicated, but Okay. So this is it. We have the ground source heat pump, and then we have the chillers, water cooled or air cooled, connected to the air handling unit. So everything is a heat pump. Okay. So air cooled chillers are heat pumps, water cooled chillers are heat pumps, but that work only for cooling. The ground source heat pump will work for cooling and heating. Okay, so that's the only difference. But I would do this. I think this is the best system, the most efficient one, and in terms of architecture, it's the less demanding because here you have a lot of monsters. We have these chillers, either water or air. So either in the basement, and then we have a cooling tower, another monster. So here we have only one monster, which is the heat pump that usually is on the basement, so we don't see that on our building. We're not aware. Yes, on the basement we have that monster. Yeah, but we don't have anything on the roof. And the setback is that this ground source heat pump has to be connected to this borehole system, and it's too expensive. Okay, but in terms of architectural design, this is the best because you don't see anything. Yes, you have a lot of boreholes there on the side, but I don't see them. And I have a monster here on my basement, but I don't see it. Here we see, probably we don't see the water cooled chiller because it's on the basement, but we do see a cooling tower, a monster expelling water, but expelling something. And then we see the air cooled chiller, another monster on the roof. Okay, so in terms of architectural design, this is the best one. It's the most expensive. It's the most efficient as well. But again, we have to make these kind of decisions. Well, here I have some pictures of what the ground source heat pump is about. Okay, so the ground source heat pump, it's a box, but the issue is all these that we have to bury. Okay, so we have to first, we have to dig. So these boreholes, we're talking about, let's say 100 or 200 foot depth. The diameter of these holes, it can be something like this, like a foot. Okay, so imagine that we have a cylinder, that it's a foot diameter, and then 200 feet in depth. Then we have to introduce those pipes. Okay, so we have 200 feet, sorry, borehole, and then we introduce 4 pipes. See that there are 4 pipes. They have a return, supply, return, supply, and return. That usually there are 4 pipes. We need something heavy because we have to go down 200 feet. So here we need to add something that is quite heavy, so that we have bending pipes. That can be done. Then we use this for sure. And at the end, when we have the pipes there, we have to fill the hole with some concrete. Okay. So we have to protect those pipes, and we fill this borehole with concrete there. So at the end, it's something very expensive, and it's something that it's buried. We don't see it. And how many boreholes do we need? It depends on the size of the building. But you see that each 4 pipes, they come from the borehole here, another one there, another one there, another one there. So at the end, we have a lot of pipes buried, and then we what we do see is this. So on the basement of our building, we will have this. Remember, this is a manifold. Okay, so here we have each 1, 2, 3, 4, 1, 2, 3, 4. Okay, so each of these manifolds is 1 borehole. So how many? 1. Okay, if you have 20 boreholes, we need 20 things like this. So it's quite complicated. The installation of these pipes. We have to dig the holes. Then we have to introduce the pipes to the hole. Then we have to introduce the concrete to protect the pipes. Then we need before doing anything else, but here we haven't done it. So this is that will be the basement, and then we need to cover this with concrete or whatever. But we have all these elements there, and at the end, on the basement, we will have this box with all the circuits. And what happens if something's wrong here? You lose it. Doesn't work. If there's a water leak, you have lost the borehole and all the money that you have spent on doing this, because you can't. It's underneath the building. So to fix this, you have to demolish the building, to remove the floor slab, and to fix a water leak that you have here. So it doesn't make sense. So if something goes wrong, you have lost one of the boreholes and all the thousands of dollars that you have invested on it. Again, it's the most efficient. We don't see anything. Once it's done and it's working well, everything is perfect. But it takes a lot of money. So that's the setback of this. And I don't see a way to do this cheaper in the near future, because you have to dig the hole and you need to do this. So there's the technology. There's now, okay, so more probably this technology will be there in 15 years. No, it won't. It will be the same. You have to dig the hole, you have to place the pipe there. So there's no way to make it more efficient or cheaper. Anyway, the alternative, the cooling tower. So we have this for nuclear plants, and we have this for buildings. So the alternative is that on our roofs, we will have monsters scanning water. So it's not bad in terms of breathing, but it's not beautiful. Nobody likes this. And the cooling tower, well, as I told you, it's quite simple. It's like a shower. We have a coil with hot water. We have a shower of cold water. We put down the coil, and that's it. And we lose the water of the shower. And this is it. Okay, so here we have another schematic view, but I have seen this before. This is the water-cooled chiller. Then we have to connect this to the air handling unit, and we have to connect this to the cooling tower. And that's it. So this monster is on the basement, and the cooling tower and the air handling unit, they are on the roof. Can we combine things? Yes, we can. So here we have a system. Okay, so here we have boilers. So these boilers are connected to the air handling units here. Here we have water chillers. Here we have the cooling tower. Here, apparently, we have the air handling unit for heating, and we have different air handling units for cooling. But we could connect everything to those air handling units. So at the end, if we look at this, we can try to understand what they are doing. And it's about connecting things. Is the boiler connected to this? Yes. So it's connected to the air handling unit. The chillers, the water-cooled chillers, they are connected to the units here, and they are connected to the cooling tower there. And there is even a connection between the boiler and the chiller. I will do that. Okay, but maybe there's a reason to do it. Why? We have to ask the one who did this. Why are you doing this? And if there is a good explanation, I will accept it. But in theory, I wouldn't connect boilers and chillers with the same circuit. Doesn't make sense. But maybe it makes sense on that specific building, because at that moment we need both systems connected. I don't know, but in theory, I wouldn't do it. But if we have this schematic view, we can understand what the engineering is thinking. Okay, so the system, boilers, chillers, cooling towers, and air handling units. Do we have radiators, radiant floors? No, that's it. Okay. So this is the system. So here we have all the elements, and we can see the connectors. At least the boilers are not connected to the cooling tower. That makes sense. Okay, so the cooling tower is only connected to the chillers. And why is this air handling unit connected to this boiler and this connected to the chillers? Why aren't yeah, I would connect two systems to the same air handling unit. That is what I would do. But this guy or this company has decided to do something different.